Here is our first language for consideration, a power n, b power n, c power n, where n is at least 1. We already had some intuition that this will not be context free because finite automaton, we know it can accept a power n, b power m, and it cannot accept a power n, b power n. The thing is, it cannot remember number of A's read when it comes to B. But if you look at PDA, using stack, it can remember one symbol. So it can remember number of A's read, which it can use to check whether number of B's and number of A's are one and the same. But by the time it exhausts B, the count of A and count of B both are lost. We do not have information about the number of A's and number of B's. Because when we start reading B, we perform pop. And we do not have any other storage. So you cannot store, meaning simultaneously pop and as well as push B, that's also not possible. So which means by the time we come over here, we do not know the count of A as well as B, and so intuitively we think there is no PDA for A power n, B power n, C power n. Because when we start reading C, I should know the count of these two. Only then we can match and say yes, they are of the form A power n, B power n, C power n. So intuitively we think with just one stack it is not possible. So now we will formally prove using pumping lemma that the language A power n, B power n, C power n is not context free. There is no context free grammar for this language. There is no push down automaton for this language. Okay. So let's use pumping lemma. So choose a string of really long length. Let n be an integer. So we choose u to be a power n, b power n, c power n. This is our string. Cardinality of u must be at least n. That property is respected. We have to choose a string of length at least this. Now we have to come up with a decomposition. Whatever way we decompose, we should show that here is one I for which the string generated is not part of the language. Okay. So let n be an integer and u is this. Let's decompose respecting the property that w, x, y, their cardinality is at most n, and wy is at least 1. Okay. So whatever way we decompose respecting this, we should come up with one I. Fine. Now wxy is at most n. Fine. So which means case 1 wxy is part of a power n. Okay. Case 2 wxy is part of b power n. And case 3 wxy is part of c power n, because decomposition could be anything. So it may so happen that wxy is part of a power n. For example, it could be like this: a power n, b power n, c power n. This a power n, let me write like a power n minus 2, b power n, c power n. This is my b, and wxy is part of this, and this is our z. Now in this we need to see what is w and what is y. Of course both will be a. Then we will talk about the pumping part. Fine. So case 4 is wxy is part of the first two symbols a power n, b power n. Case 5, wxy is part of the next two b power n, c power n. Remember, wxy is at most n, so which means it cannot span three symbols because this itself is n. So wxy, it cannot span a power n, b power n, c power n. So it can only contain at most two symbols. So wxy can contain at most two distinct symbols from sigma. Okay, but we have no clue about the decomposition. So decomposition could be, for example, you take a power n, b power n, c power n. This b could be a and wxy is part of this, and b power n, c power n is this. And when it is part of, say, a power n, b power n, it could be something like this. So you have a power n minus 2, a square, b power n minus 5, b power 5, and c power n. So this could be v, and it is at most n. So which means, let me take this to be 3 followed by b square. So which means n minus 5 plus 3 plus 2, all this is part of wxy, and this part is z. Okay, so when it is having a and b, decomposition could be any form. And in that, we have to see w and y. Similarly, in this, we have to see w and y. Okay. So similarly, when we have b power n, c power n, we have to see w and y. One of them can be empty. The property only says together it is at least 1, which means w may be 1 and w may be just a and y may be empty. What am I saying? If you look at this further, it may be the case that it is a followed by a b power n minus 5 b cube, and this is our w and this is our x, and y is empty. It only says together at least 1, so which means either this or this must be non-empty. Okay. So one of them must be non-empty. So decomposition could be anything. Okay. So let me repeat this part to show that it is not context free. What we are applying the contrapositive of the lemma. So which means let me choose a string of sufficiently large length. So here is a string a power n, b power n, c power n respecting this property. Now whatever way we decompose respecting this, we need to come up with a contradiction. Now decomposition can be anything, which is why I am looking at the possible cases that wxy is part of the first a or b power n or c power n, or it can contain at most two symbols because this length is at most n. So it may be part of a power n, b power n, or it may be part of b power n, c power n. It cannot be the case that it has a, b and c. Okay. Now in each of this, let's identify one I for which we arrive at a contradiction. Let's look at the first case. Let me choose I to be 2. Now remember, Wxy is part of this, which means if you substitute I is equal to 2, what will happen? You will have more A's compared to B's and C's, because it is just part of A. So this implies that more number of A's will be more A's than B's and C's. So this implies that the string is not of the form A power n, B power n, C power n. Correct? For example, you take something like A square, A power n minus 2, followed by B power n, C power n. Let's assume this is V, this is Wxy, and this one is Z. Just an example, because we can get any decomposition. And in this, W is something, Y is something. So let me say W is AA, and followed by A power n minus say 5, and on this side let me say this. So which means this one is W, this one is X, this one is Y. The rest is the same. Okay. Now you see that if you choose I equals 2, then what will happen? You get A square, AA square, A power n minus 5, A square, B power n, C power n. Now this clearly not part of A power n, B power n, C power n. Okay, this is just an example, because one can come up with any decomposition. So you choose I equals 2, whatever may be the decomposition, you get to see that number of A's will be more compared to B's and C's. So naturally you get to see that the string that is generated is not part of this. So now what is that we have concluded? Here is a string which is part of L, and whatever way you decompose respecting the pumping lemma property, we generate a string which is not part of L. And that shows that our assumption that it is context free is false. So you conclude that A power n, B power n, C power n is not context free. Okay, so on the similar line, let's analyze the other cases. Let's look at case 2. For case 2 also substitute I equals 2. Since Wxy is part of B power n, now you will see that you will have more B's than A's and C's. And for case 3, again I is equal to 2. You will see that there will be more C's. Let's look at case 4. So in this case, again choose I is equal to 2. Now Wxy is restricted to A power n, B power n, and so it may so happen that say for example, again it's an example, you take say A power 4, B power 4, fine, and Wxy is precisely this. So it may be like A square a square, b square, b square. This may be w, this may be x, and this may be y. Okay. And it only says one of them must be non-empty, or it can even be like a power 4 is w and b power 4 is xy. Now if you choose I is equal to 2, in this case number of a's will be more. In this case, more a's. If you choose this, then this will have a power 4, this will have b power 4. Okay, then you will get something like a power n plus 2, b power n plus 2, followed by c power n. A and b may match, but it will not match with c. Okay. In this case, more a's and b's. So it can happen like this, or w may be empty. Something like a power 4 is x and b power 4 is say y. In this case, more b's. So it may so happen that you will have more b's or more a's, or both a's and b's both are not matching with c. But whatever it is, in all these three, it will not match with c. In this case, more c, so it will not match with a and b. In this case, it is more b, so it will not match with a and c. So on the similar line, choose I is equal to 2 for this. We clearly see that count will not match with the number of a's. So you may have more b's or more c's, or you will have equal number of b's and c's, but that will be more than the number of a's. But in all sub cases, you see that it will not match with the number of a's. Fine. So far what we have done is we chose a string, and then whatever way we decompose, we looked at possible cases as part of the decomposition without assuming any specific example that this is how w will be, x will be, y will be. No. Because of this property, we know w, x, y can fall into one of these cases. Accordingly, for each of them, we say here is one I for which the contradiction comes. You can choose different I as well. For example, I is equal to 0 also one can choose. I is equal to 4 one can choose. You can choose I is equal to 0 for this, I is equal to 2 for this, I is equal to 10 for this, because it only says there exists I. You choose one I for which here is a string which is not part of the language. Okay. But interestingly, if you choose I is equal to 2, and you get to see that we arrive at a contradiction. So whatever way you decompose, you get to see that there exists one I. For example, I is equal to 0, then you get a contradiction. Take I is equal to 2, you get a contradiction. Take I is equal to 10, you get a contradiction. Fine. So you get to see that there exists one I, at least one I, for which the contradiction comes. Therefore, this language is not context free. Fine. And with this, one can also prove related languages. For example, language consisting of set of x such that number of a's in x is same as number of b's in x is same as number of c's in x. Okay. If you look at this, a power n, b power n, c power n is a special case of this language. Let me call this one as L prime, and you see that L is subset of L prime. Since L is not context free, implies that L prime is not context free. Okay, so proving one language, one can also prove the related ones. A superset is set of all strings over A, B, C such that number of A's is same as number of B's is same as number of C's. Same proof, because proof only says choose a string. Choosing a string is with our control. Only thing is the length of the string must be at least n. We still choose this and run the argument because a power n, b power n, c power n is a string which is part of this respecting this property. Okay. So this shows that the same proof works for L prime as well. Fine. So let's look at a couple of more examples and appreciate the power of pumping lemma for CFL.